Yes, each side of this page is going to be one full problem. Each side looks the same, so it doesn't matter which side you're working on. But you can see how much stuff there is. So this one problem is going to take a while. We're going to fill out everything, and then hopefully we'll have a really good graph because we'll have so much information. Here's the first equation we'll deal with. F of x equals x cubed plus 6x squared plus 9x. And basically our job is to answer all these questions and graph it. X cubed plus 6x squared plus 9x. Okay, I guess we can start with the algebra stuff. X-intercepts. What do we know about x-intercepts? Or how do we find x-intercepts?
Y is 0.
Good. Y is 0. So we'll set y equal to 0. This one's nice enough where I can factor it. And rather than a number out front, this one has an x out front. So that does mean we get an x equals 0 as one of the x-intercepts. So x equals 0 and x equals -3. Do you remember anything special about what this is called or what's going on here? It's a double root. Do you remember what that means when it comes to the graph? There's a bounce there. So all that stuff that we sort of know, kind of know in the back of our brain, if we'll remember that, it'll help build this whole picture. I guess the good news is we know enough that if we forget a couple of things, we'll probably still be okay because a lot of it overlaps. But the more you know, the better off you are. Y-intercepts would be set x equal to 0. That's easy. That would just be 0, 0. Asymptotes. I don't think this thing has any asymptotes because that's a polynomial. So none on the asymptotes. So that's kind of where our pre-cal algebra 2 reasoning would stop. We would plot those points. We would know it's a bounce. We'd probably have to plot some more points in there to get a feel for what it looks like. Although it's x cubed, so maybe we've done enough of those to have a good enough feel. But now we're going to do some calculus. So first derivative would be 3x squared plus 12x plus 9. And we want to get some intervals. So we want to do all the first derivative stuff. Increasing, decreasing, max and min. All that stuff. So let's set it equal to 0. We can factor out a 3. Of course, a 3 out front does not lead to any zeros, right? That's just a number out there. Hopefully we can still factor. X plus 3, x plus 1. So x equals -3 and x equals -1. So those are critical points. Those are potential maxes and max or mins. But I think I want to do a number line here. There's not much space for it, but squeeze one in here. So my number line, you could almost get away without one because of how this box is laid out here. But there's an interval from -∞ to -3, -3 to -1, -1 to infinity. This is a generic worksheet that we'll use several times to plot stuff on. So sometimes there's extra blanks. There's usually some stuff that has none on it because this is just a template that we use to fill out as we go. It's not specific to this problem. Test value. Okay, so this is like walking us through the first derivative test here. negative 4, negative 2, and 0. Again, you could get by without the number line because this is walking you through it, but I'm used to the number line, so I still want to see it. All right, if I plug in negative 4, I think I would use the factored form here. If I plug in negative 4, I get negative times negative equals positive. Which my conclusion then, so what's my conclusion? If f prime is positive, how does that help me with my graph? What's f doing? F is increasing. I plug in negative 2, I get positive times negative, which is negative. So f is decreasing. Plug in 0, positive times positive is positive, f is increasing. And maybe the words are good enough for you to tell what's going on, but a little picture sure helps the brain sometimes. So increasing to decreasing to increasing, and the picture helps me see that there must be, and maybe on the number line, there's a relative max at negative 3 something, and a relative min at negative 1 something. Because, and we've written this several times now, it was on the test, we talked about it yesterday, you used the words in the examples we did earlier, a relative max because f prime changes positive to negative. And a relative min because vice versa. F prime changes negative to positive. But I want to point, because I'm headed for, the goal of this is to get a really nice, accurate graph down here at the bottom. So I need the x value to go with that. So maybe out to the side somewhere, I need to figure out what f of negative 3 is. All the way back at the beginning. Negative 27 plus, 9 times 6 is 54, minus 27. Oh, that kind of worked out for us. Negative 3, 0. F of negative 1 should be a little easier, just smaller numbers. Negative 1 plus 6 minus 9. Would be negative 4. All right, so we got a max, we got a min, we got some intercepts. Starting to feel pretty good about this. Some people will start graphing the stuff as they know it and making sure it fits. Maybe we should do that. Let's graph what we know, because if we end up graphing something that doesn't look right, we need to know that so we can go check and see what's happening. Our intercepts, 0, 0, negative 3, 0. We also said negative 3, 0 was a bounce, so we'll need to be careful about that. We have a max at negative 3, 0. Oh, but that makes sense. If that's a bounce, it makes sense that there would be a max there. There's a min at negative 1, negative 4. Okay, that sort of fits with what we think is going on here. But let's keep going because we don't have concavity yet. So second derivative, I just drew the arrow from the first derivative because you gotta. So we sort of drilled down into the details of first derivative. Now we got to back up, go back to the polynomial, come up with the second derivative, and then do the second derivative stuff. 6x plus 12. So we'll set that equal to 0. X equals negative 2. Again, I wish there was a spot for number line, but the table is good too. Negative infinity to negative 2. Negative 2 to infinity. Again, sometimes there's more blanks on the page than you actually need. Let's see, test value, we could go with negative 3. Test value on this one, I'd go with 0. Plug those into the second derivative. If I plug in negative 3, I get negative. So f is concave down. Plug in 0, I get positive. So f is concave up. I should be careful. I wish it had said conclusion about f, because you don't want to just write concave down. What's concave down? Some of you lost points on the test because you had said things like it's increasing. Like, I knew what you meant, and you were right, but you got to specify: is f increasing? Is f prime increasing? Because those are different things. So point of inflection. When concavity changes, the point of inflection at x equals negative 2, which is good for the x value, but if I want to put it on the graph, I need to figure out what f of negative 2 is. So all the way back to the original. So negative 8 plus 6 times 4 minus 18. Lots of math here, mental math. Let's see, that would be negative 8 plus 24 is negative, is positive. 16 minus 18 is negative 2, I think. So negative 2 is a point of inflection. Oh, that fits on the graph with what we think is going on. It's not completely standard across everywhere, but a lot of people use a little x for a point of inflection. That way you can kind of keep straight with what all these points are. You start putting them on the graph, and some people will label them so that when we go back later, we kind of know what we're doing. Max and min. That origin point, that was just an intercept, so that wasn't a max or a min. I think we're ready to graph this thing. Let's go ahead and answer the following, or the last few questions here. As x gets really big, this is more for stuff that has like rational functions, stuff with denominators. As x gets really big, the function goes to infinity. As x gets toward negative, I think about this one a little bit. If I plug in negative infinity right there, what's this graph headed toward? Positive or negative infinity? Negative infinity. So as we go off on the right end, we're going up. As we go off on the left end, we'd be going down. Well, again, that sort of fits with everything we have. Do you remember about even, odd, neither? The shortcut is all the exponents are odd versus all the exponents are even versus sum of both. And this helps graphing because odd has symmetry with the origin. Even has symmetry with the y-axis. And neither doesn't have any symmetry. Well, this has x cubed and x squared, and x. So This is neither. So that this only helps if it has one of the, if it's odd or even, that gives you some symmetry that will also help you graph it. Alright, so we're increasing up to the max, but concave down. This is the next point. All concave down until we hit our point of inflection. After that, we're concave up, but that fits perfectly with the points we have. So I think this. So there's our graph. So that's using all of our calculus knowledge thrown together to do a graph. First derivative stuff, second derivative stuff, all the intervals, max and mins, points of inflection, putting it all together to get a really nice and accurate looking graph.